So, first of all, I want to say, how many of you are ham radio operators in the audience? Quite a few? Right. So, first message is, please be gentle. You may notice that for the very first time, I've put in my talk my ham call sign, but notice that it's a foundation license. I only just got my license recently, so I'm a raw beginner with radio. So please be gentle. And so this talk is about the work we've done with developing radio technology, telemetry radios and image transmission radios for the UAV project. Last year I talked about Rescuing Joe, our project for the Outback Challenge to create a UAV for finding a lost bushwalker in the Outback up in Queensland. That's the plane. That's just after the competition, after we rescued Joe, or at least we found him. But we needed to do a lot of work with radios, and because I didn't know whether we were going to crash on takeoff, when I was submitted this talk, I thought I'll submit it about something that I know works, which is our radio technology, and I thought it also might be of interest to people, rather than saying, you know, putting in a talk about how we did in the Outback Challenge and then just saying we crashed on takeoff. Luckily we didn't. So, communication with UAVs. Communicating with UAVs is a little bit different to communicating over the internet. There are some fairly specialised requirements. We have real-time flight data, telemetry data coming down from the UAVs, and that's typically a few kilobytes per second, and that's things like your attitude information, the raw sensors, your barometer, the navigation information, what the plane, where it's trying to go, where it currently is, all that sort of information. And it's very repetitive information. Each packet is different, but it's very similar to the last one. Sort of, you know, the gyroscopes don't move an awful lot between packets, which means you can afford to lose a few packets, and that's fine. You need to have a very reliable uplink for controlling the aircraft. You need to be able to command it to come home, to change its altitude, to do whatever you need it to do. And so the packets that you're sending up are much less frequent, but they need to get through with a high degree of reliability. The bandwidth is typically of the order of 3 kilobytes per second downlink. The uplink is much lower than that. It's more like of the order of bytes per second to tens of bytes per second. So it's quite asymmetric. But as I said, the uplink data, you really have to get it through. And the data is quite repetitive. Now, we adopted a protocol called the MAVLink protocol, the Micro Aerial Vehicle Communication Protocol, which is a bit of a standard within the amateur autopilot community and is starting to be used by some of the professional autopilots as well, commercial ones. The AR drone has just started to adopt MAVLink, for example, and some of the other, you know, more expensive ones are starting to use MAVLink as well, which is nice. I wrote a little generator for MAVLink. It's basically an XML file that defines our protocol, and then there's a Python script that generates a Python implementation and a C implementation and a C# implementation and various other language-specific implementations for different platforms. Okay, so that's our basic communication problem. This is a rough schematic of what our UAV looks like. There is a Panda board running Linux. That's a dual-core gigabyte of memory type Linux box. It was running Ubuntu. It has an SSD, 64 gigabyte SSD attached to it. We have we had only one camera in the final configuration. This was a slightly earlier draft. 2 radio links, which is what I'm concentrating on today. One at 5.8 gigahertz, which uses this sort of radio technology. This is a Ubiquity Bullet, a 5.8 gigahertz Ethernet bridge. It can range from about 1.5 megabit up to sort of 100 megabit type link. We ran it at its most conservative settings, known as MCS 0. So you're running it at the lowest possible speed for maximum possible range. And then we had 915 megahertz radios, which are these types of little radios. And the first half of the talk is really talking about the development of the firmware for these radios. And what I'll just show you first of all is something many of you have seen before. These are XBs. How many of you have used XBs before? Heaps of you? Yeah, XB is really popular in the hobbyist community. And we sort of had a bit of a love-hate relationship with XBs. You know, they're ubiquitous, lots of people have them. They're a bit pricey for what they do. The range is fairly poor. even the XB Pros and even the Digi Extends and things, the claimed ranges tend to be an awful lot longer than what you actually get. And they've got lots of little quirks in them. The most annoying quirk, which I'm sure many of you have hit, is that when they initially boot, they start for the first couple of seconds in bootloader mode. So if you happen to squirt any data down the serial port for the first couple of seconds, it overwrites the firmware, which is really inconvenient because you've then bricked your device. You need to de-brick it. And so we had this long de-bricking procedure because what tended to happen was somebody would forget to attach the radio, right? And then they turn on their aeroplane and then they plug the radio in and it's already squirting data. So just delaying the start of the telemetry stream doesn't do it. Very annoying and not open. The inners aren't open. The protocols are reasonably open, but if you want to hack on it and extend its capabilities, there's very little you can do. So we were interested in developing a telemetry radio for our sort of applications for multicopters and small fixed-wing aircraft, and also for rovers, ground rovers, which used as an open protocol and also open implementation, but also got much better range and performance in lots of different ways than what we could get out of things like the XB. Okay, so that resulted in a little radio which we call the 3DR telemetry radio, called the 3DR1 because 3D Robotics was the first, they were the designers and the first company to manufacture it. These radios are in fact now manufactured by 6 different companies, which is great. So a whole bunch of other companies have taken the software that we've produced and the hardware designs and either done their own hardware design with a slightly different twist on the form factor or whatever, but it runs exactly the same software. Now the basic radio itself, it's an interesting little radio. I'll just hold up one of them. So this is a USB variant of the radio. So that's got a USB connector on it. And then I've got another one here. Here's an XB form factor with TTL serial radios. So they're relatively small. There's even, if you take off the USB connector for the air radio, it's about half this size again. So they're relatively small radios. Not the smallest ones you can get, but really quite cheap little ones. And certainly compact enough to fit in a small multicopter or UAV. Now these radios are interesting because they've got they're a system on a chip. They've got a little embedded microcontroller, and it's an 8051. And this was my first experience programming anything of the scale of the 8051. How many of you have programmed something like an 8051 before? Quite a few of you. Okay. Well, my background was on systems programming where you worry about whether you should have 16 gigabytes or 32 gigabytes of memory in your system, for large file servers that might, take up a room or whatever. It's the Samba or an rsync and those sort of things. And it was very interesting working on a chip where the first level memory was 128 bytes, which is really rather constraining. And then there's second level memory, paged memory at 56 bytes, and then there's a third level sort of secondary page memory, which is 4 kilobytes. Gosh, lots of memory. We have 7 bytes of that left for the next, the final features. So at the moment we're down to 7 bytes remaining memory on this system. So we're really pushing this chip to its limits. It's got a 64 kilobyte EEPROM to put the firmware. It supports lots of different modulations in hardware. So this is very different to what David Rowe was talking about in his talk yesterday, where his hardware is doing all the modulation directly. It was incredibly impressive what he was doing there with those radios. And Joel afterwards with what he did with the Arduino. In this case, the chip actually is able to do the modulation for you. So you can just basically give it a bunch of data and start DMA transfers, and it will then modulate that data and squirt it out the RF part, and you end up with the data going over the wire, and you can over the air, and you can choose FSK, frequency shift keying, or GFSK, Gaussian frequency shift keying, or OOK for on-off keying. And that gives you a bunch of different modulations available very easily. It has a TTL serial interface. So basically you can just squirt bytes at it using TTL serial, and that means it connects very easily to our little autopilot boards, or you can connect it directly to a GPS if you want to. If you wanted a self-contained little navigation beacon type thing, you could connect a GPS directly to one of these little radios and throw it up in a balloon or something and have a really neat little beacon. Quite low power, the chip. Except of course when it's actually transmitting. When it's transmitting, of course, it has to actually use the power required for the transmit part of the radio. The base chip, the SI1000 system on a chip, is available in 4 variants: 433 megahertz, 470 megahertz, 868 and 915 megahertz. For our particular use in Australia, 915 megahertz was the most useful, because in Australia, in the ISM bands in 915 to 928 megahertz, you can transmit up to 30 dBm EIRP, so 1 watt basically you can put out. In the US, you can actually do a bit more, because there's a strange rule in the US where they don't count don't count up to 6 dB of antenna towards the EIRP calculation on the ISM band. So you can actually, with these radios, do 36 dBm, which is a lot of power to be putting out EIRP. That's the effective isotropic radiated power. That's the effective amount of power in one direction if it was going out in all directions. And when I got my ham license, I was really surprised that ham license powers aren't based on EIRP. It's just, much antenna as you like and it doesn't count. It's really surprising. Anyway, that's how it works. So this original radio was based on a maximum of 20 dBm transmit power. It's 100 milliwatts it will put out. And that will give you, with a little omnidirectional antenna on it, you can certainly get several kilometres of range. People have got up to sort of 10 kilometres or so. We've tested it between hills in Canberra, 10 kilometres apart, and managed to get clean signals coming through. Very much depends on your background noise. And the receive sensitivity, it'll receive down to -121 dBm, which is really quite incredible. And we wondered originally whether that was just a manufacturer claim, that they could do that sort of receive sensitivity, but we got it into an RF lab up in Queensland. Seppo at RF Design very kindly tested stuff on his lab, and we found indeed we started getting packets at -121 dBm, which is really quite remarkable. We found amazing that it actually has that sort of receive sensitivity in an incredibly cheap small package like this. Okay, so that's the basic hardware. So what about the software? I mean, it's really important what software you put on these radios, and the aim of this project was to create an open source telemetry system, and the difference between the open source and non-open source is what's the firmware. These radios come with an incredibly simplistic firmware that comes from SI. And that firmware is basically, if you put bytes in the serial port, it will copy them out into the radio, into the ether. And if you receive bytes, if it sees something coming in over the radio, it squirts it out the serial port. It makes no attempt at all to avoid talking while the other guy is transmitting. So both transmitting at once. No attempt. No attempt at frequency hopping, no attempt at time division multiplexing, no attempt at all to do anything sane. It just has a way of getting bytes off the serial port and into the air, or vice versa. And that really is no good for the sort of applications we have. First of all, it immediately violates a whole bunch of regulatory rules. You have to jump between lots of different frequencies if you're using, for example, the 915 megahertz band in Australia or the US. You have to have 50 different channels hopping between, with a maximum dwell time of 0.4 second in the US, 20 channels in Australia, and there's different rules all over the world as to sort of how long you're allowed to sit on a frequency in order to be able to share the band with other users. It makes no attempt at doing things like listen before talk, to listen to see whether somebody else is talking before you start talking. It just transmits when it receives a byte coming on the serial stream, and it has really no encapsulation. It just throws the bytes out there and hopes that somebody's listening, and no attempt at all to comply with any licensing rules whatsoever. So it was a very basic thing. It was a good example code though. It was very simple, just a few hundred lines of C code, and it gave you a basic, transmit receive, but no good for the sort of application that we had. So I started digging into programming for the SI1000, which was a real adventure. we were using the SDCC, Small Device C Compiler, which is a very different sort of C compiler than what I'm used to with things like GCC. It has a whole lot of special stuff for embedded coding, which is very nice. Nice stuff for critical sections, marking critical sections very nicely. A support for Booleans being stored as single bits. In a special 128-bit Boolean register that has, you can have up to 128 Booleans in your program, but if you have 129, bad luck, you won't compile. It's not stack-based by default, which I found very interesting. I'd never dealt with a non-stack-based C language before. And so we need to declare, or by default it's not stack-based, we need to declare a variable as a local variable in a function. That doesn't get stuck onto the stack, it gets allocated space in global memory, just like any other sort of variable. And that means functions aren't reentrant by default. You can't do, Fibonacci by recursion unless you mark the function especially as being reentrant, in which case you better be careful because you don't have much stack, you've only got a few bytes of stack typically sitting above you, and so you can very, very quickly run out. And so you really want to very carefully lay out your program. So you basically need to tag every variable with what type of memory. Variables that you need to be fast, you tag as being in the first 128 bytes of RAM, and the compiler will dutifully pack it into that first 128 bytes. Variables that don't have to be quite so fast, you can say they can be in the next 56 bytes of RAM, right? Because I don't mind if it takes a few extra instructions to get at that bit of memory. And variables that don't have to be fast at all can go in the 4K, enormous chunk of memory that you've got, which we use for things like serial buffering. And large, other things that we're dealing with the protocol. But all of your sort of loop variables and things you need to tag. So you get some very interesting declarations where you have sort of a pointer to an integer, and the integer might be in fast memory, but the pointer to the integer is in slow memory, and you get these very long declarations of variables. And it can make for some very interesting prototyping things. And unfortunately, the compiler doesn't check that they're all compatible. So I wrote a little Python script that parses C and cross-checks all of the prototypes across the code as being compatible with each other and throws an error. Because otherwise, you get some very bizarre errors if you mix up your prototypes and you pass the wrong sort of memory across to a function. It just doesn't work. But other than that, it was a very interesting environment to work in. I also wrote a little script that analyses how much memory you've got left in each type of memory. We're down to 7 bytes of RAM left in the CPU at the moment. We were down to 4, but we gained 3 bytes by upgrading the compiler, which is great because it means we can fit a new parameter in now, which is really wonderful. But it's a different sort of programming to what I've been used to. Okay, so what about making this thing useful in a real world environment? You can't all talk at once in the radio. These are a single, only one person can transmit on a particular frequency. It doesn't have, a separate receiver and transmitter on different frequencies. The chip just can't do that. So you're only on one frequency at a time. So only one person can be transmitting at a time if you want the data to get through. So you've got to avoid collisions, avoid talking at the same time. And there's lots of different ways to do this. The simplest is called time division multiplexing. And so that's what I went for, where basically you divide up time into slices, and one of the radios gets a chance to transmit in this first slice, and then the other radio can transmit in the next slice. So we end up with a little diagram like this, where we have a little window at the beginning, the red bit, where the first radio is allowed to send and the other radio is receiving. And then there's this blue bit in the middle, which is a silence period, where we have this small period of time where neither radio is supposed to be speaking, assuming that they've both got their clocks synchronized correctly. But if their clocks aren't quite synchronized, that's to allow the tail end of the transmission of the last packet from the previous guy to edge across into this silence period where the other guy thinks that everything's supposed to be quiet, but in fact, because the clocks aren't quite synchronized, he wasn't being quiet. Then it switches across and the first guy ends up in receive mode and the second guy ends up in send mode. And then there's another silence period and then it keeps going. So you switch backwards and forwards between them. And you'll notice that I've also marked here in the middle, these two lumps here as frequency n, and those two lumps as frequency n plus 1. And that's when we get into the frequency hopping, which I'll talk about in a minute. Timescale-wise, the send window in a default configuration for these radios, the default configuration is that they talk at an airspeed of 64 kilobits, a serial UART speed of 57 kilobits, and but with error checking, that I'll talk about a bit later, the practical data throughput rate is actually 32 kilobits, because you lose half with the error checking. And the send window is 6,200 ticks. A tick is a 16 microsecond period. It's about 100 milliseconds as your send window. Then the silence periods are typically about 5 milliseconds. When it starts up, it calculates all of these numbers based upon the configuration that the user has given the radios. So the user is able to put in all the parameters for the hopping frequencies and the speeds, the air rates and the serial rates, etc. Now, those of you who are listening to the numbers may have noticed that the link is oversubscribed. Any of you noticed that? So notice that our serial rate is higher than the data transmission rate, and that's quite deliberate. And we actually have some flow control information that's able to cope with the fact that the link is oversubscribed. And it works very well because of the fact that usually the link is sending a lot more data in one direction than the other. And so what we need to do is have a slight twist on TDM where we allow these periods to be not the same for each transmitter. So one person can get slightly longer time slices than the other. So the way we do that is, this is how we pack the data that we send out over through the air. We have up to 250 bytes of data there, and then we have a 2-byte trailer sitting at the end. And this 2-byte trailer, these 16 bits, consists of this little bit field that you can see up there, where the first 13 bits of the bit field is I call the window. And that is how many ticks, how many 16 microsecond ticks the transmitter at the time that they sent this packet thought was remaining in their transmission window. Okay, so if we go back to this transmission window in the previous one, the red section, it's sending lots of packets, 6, 8, 10 packets in that red section on the left there. And each time it sends a packet, it puts this little trailer on it which says how many ticks it thinks are remaining before we're going to switch over to the next one. And those 13 bits mean that any one packet getting through is enough to synchronise the clocks between the two radios. Because we don't need absolute time synchronised. We don't need GMT time or anything like that. All we need to know is that they both agree when the next switchover is going to be, right, to the next TDM phase and the next frequency. And so we just need to know how many 16 microsecond ticks of our little timer are before we switch over. So that's what we do there with those 13-bit window. And we also have a few extra bits which are what give us the adaptive timing. There's a bit called the bonus bit, and that bit is used when a sender, it's their send window, so they've got permission to send at the moment, but they've got no data, right? Which is very common, because the ground station usually doesn't have nearly enough data to fill a full send window. He's only got a few bytes, occasionally sending a command and a heartbeat, that sort of thing. So what he does was he sends a packet with the bonus bit set, and the bonus bit says, I'm yielding the remainder of my time slice to the other end. And that means the other radio is then able to transmit not just for the remainder of the first radio's time slice, but also right through the silence period and right up through their next time slice. Right? Which means you actually only have a very small period of time where the ground station has grabbed the transmit token, if you like, and is transmitting, and you end up with a practical efficiency from the air data rate down to the data you can actually get through of about 85%, which is not bad on a bidirectional link. so we can actually get quite a lot of data through reliably if most of the data is coming in one direction. But as soon as there's data that needs to upload, you're uploading a mission, a set of waypoints or some control information or a new set of parameters, and you've got a flood of data coming upstream, it immediately adapts towards that and can shift towards mostly being the ground station transmitting and switch back immediately to mostly the plane transmitting. And it costs you about 15%. We could get it down much lower than that, but basically at that point, the various tolerances of our clock and things, it's getting a little tricky, and so it wasn't worth the effort to push that up to sort of 90 or 95, 85 we were quite happy with. Now, there's also an extra bit, the command bit. Now that's something that we added later, but it was extremely worthwhile in the protocol. How many of you have used Hayes command set modems, AT command set? Most of you would have used it in your careers, yes. So the AT command set, very, very useful, and so we decided to implement configuration of these modems via an AT-like command set, although we extended it a little bit. And the biggest extension was the addition of this command bit, where you know the AT command set controls the local modem. Well, the RT command set for remote controls the remote modem. And anything you can do with the AT command set on the local radio, you can do with the RT commands on the remote radio. So RTI, RTS 7 equals 15, whatever, all of that is available, which is extremely useful when there's a plane flying about and you want to adjust the parameters, the error checking that it's doing, and you don't need to land the plane and go up with a USB cable or whatever. You can just reconfigure it remotely while it's flying around, which is really handy as long as you get it right. This is where having multiple radio links up to the plane is great, but I have quite often broken into it and modified the configuration in flight to change the error checking parameters or whatever, or to turn on more debugging. Extremely useful. So that's what that command bit is for. And the resend bit is for increased reliability of commands going to the plane. It's supposed to be a transparent serial stream, right? The idea is that you have radio at either end, you inject bytes in a TTL serial port at one end, they come out the same at the other. But you can lose packets. It's difficult to do a transparent serial stream when you can lose packets. And acknowledgement packets are a great pain because any acknowledgement scheme requires that you have two-way communication. And we wanted all of the features of this radio to work when you only have one-way communication, right? Because it's quite common with a UAV to lose either the uplink or the downlink, but you still got the other. If you've lost the uplink, you still get the telemetry data telling you where the plane is, the GPS, for example. And if you lose the downlink, you've still got the uplink information, potentially, to say, come home, please, to tell it to turn around, right? So you can still get commands through. And so instead of using acknowledgements for higher priority operations, the ground station, before it sends a packet to say that you've now, a bonus to say you can take over my time slice now, it can resend the last chunk of data with a bit to say this is resent data, which means don't inject it into the serial stream at the other end if you got my last packet. Right? You can tell which it is from the checksum actually on the packet. You can tell whether the particular packet had already got through, a checksum and a sequence number. But that allows us to resend the command data an extra time, and that opportunistic resend is on the low bandwidth uplink, and we don't do that on the high bandwidth downlink, while still maintaining, from the high level application point of view, the transparent serial behaviour. So, and the note that this all works one way was partly for Keith, because Keith Packard, I was talking to him a lot about his little radios, and one of the reasons he wasn't thinking of doing frequency hopping was because he didn't think it would work if you only had a one-way link. But in fact, all of this stuff works, including all the TDM and the frequency hopping on one-way links. Okay, so frequency hopping. So why do you want to change frequency? Well, it allows more users of the same band. So you can have a lot more users who don't need to coordinate beforehand to pick frequencies. They can just, pick a network ID which gives you some sort of hash you put over the data, and then they can all just use the same band, and because they're jumping frequencies all the time, they only collide for very short periods, right, if they collide at all. It also is required for compliance, and these two reasons are strongly related. the regulators like radios to have low interference potential, as it's called. You know, there's the LIPD rules in Australia, the low interference potential devices, which are devices that are unlikely to interfere with each other. And if you don't want to get a special license or a ham license, you just want to use the class licenses that are available to everyone, then you have to follow these rules, which specify things like maximum time you can spend on any frequency and minimum number of channels that you operate over and the width of each of those channels, etc. So in Australia, on 915 megahertz, you have to hop over 20 frequencies, and in the US, on 915, you have to hop over 50 frequencies. And so our default configuration, we hop over 50 frequencies, and we're compliant with both US and Australian regulations, because our default configuration has the frequency band set to 915 to 928, which meets both US and Australian band regulations. Okay, so how do you do frequency hopping in a little radio like this? Luckily, it's very easy. There's a register in the radio that says what channel to hop on. So you've got a register for the base frequency, the starting frequency, or in fact several registers to give the base frequency. And then you've got a register for the channel separation, the gap between channels. And then when you want to change channel, you just write to a register and say, I want channel 17 now. And it takes the base frequency plus 17 times the channel separation, and that's your current frequency. And it happens very, very quickly. You can frequency hop at kilohertz if you wanted to, though we don't hop nearly that fast. We typically hop frequencies at around 50 hertz or so. And so we're jumping between frequencies of that sort of order. Actually, we're often less than that. Depends on what bit rate we're running at. Okay, so that's basically frequency hopping and TDM. Oh yes, how do you choose your channels? We create a randomly ordered set of channels at startup, which we just basically shuffle a set of data, a random shuffle of the data, based on a network identifier. So you configure in the radio what network identifier you want, a 16-bit number, and I think actually it's now a 32-bit number. And then if that channel identifier shifts slightly the base frequency, just by a little bit, by sort of a quarter of a channel, up to a quarter of a channel, and it also changes the order of all of your channels so that other people with a different network identifier are going to get a different set of channels that they're hopping over. And it means you can have lots of radios out at the one location, and you really get very little interference between them. It works incredibly well. And we switch channels at the end of each TDM cycle. But there's an interesting problem which took me an embarrassingly long time to really solve properly, which is the initial search. Because you turn on the radio in the plane, you've got the radio on the ground, and you want to initially gain lock. But the two have no idea what frequency the other one is on. You've got 50 different channels. So how do you initially lock so that they're starting at the same pattern? And it turns out that the solution is incredibly simple. Each radio, when it hasn't had lock, which means it hasn't received a valid packet in the last n seconds, where n might be, say, 10 seconds, then it goes into this scan mode where it's looking for a partner. And what it does is the transmit side stays exactly the same. It hops frequencies, right? But the receive side changes frequency very slowly, only once every few seconds. That means that the other guy is hopping around all the channels really rapidly, and we're just moving channels very, very slowly. The other guy catches up very, very quickly, right? Within sort of one cycle, typically within a second or so, he catches up to us, and as long as he gets one packet through, if you receive one packet, you're set. Because you know what frequency that packet was on because you received it. And you only receive on the frequency you're listening on. And that packet has the trailer with the 13-bit number, which tells you how many microseconds he thinks is remaining in his window. So any one packet getting through allows the opposite radio to completely synchronize on the frequency hopping and the TDM, which means you then have all the information you need to be in sync from then on. And the clocks on these things, even with the different altitudes and different temperatures, where the crystals aren't quite great, it will stay in sync good enough for minutes. And that means you only have to get through sort of a packet every few minutes to keep in sync for this frequency hopping and TDM. So it really works very well. Okay, so what about error correction? The next step is what about, we're sending, say, 250 byte packets. If you get one bit wrong, then a checksum over the packet will be broken, you'll lose the whole packet. And in fact, that may contain dozens of Mavlink packets, and that's fairly bad to lose that. So what you really need is an error correcting code. And you need to be able to correct bit errors. And there's lots of research around error correcting codes. I was mostly looking for one that could fit on this tiny CPU, which means these CPUs have 64K of flash, so big constant tables are good. Anything that involves lots of CPU or dynamic memory allocation is bad. And the one that popped out to me was called the GOLA code, a 2312 GOLA code. And that's actually, we used the 2412 extended GOLA code eventually, but much the same thing. Which I was very pleased to see was actually the same one used by Voyager 1 and 2. It basically means that the computing power that Voyager had in being sent off into the distance is basically the same sort of computer power that we now have on these little radios. With the 8051 microprocessor, it's almost the same vintage too. But anyway, I thought it was really nice that it was the same one. There may in fact have been better error correcting codes we could have chosen. Talking to Keith Packard earlier today, he thinks we might have been better with a particular form of Viterbi code, and I've been looking at his Viterbi code, and we may be able to do a little bit better. But this one certainly worked very well. It allows us to correct up to 3-bit errors per 12 bits of data, but it doubles our payload size, so it halves our bandwidth. It means that we only send sort of 125 byte packets and the rest is error correcting code interleaved in with the data. But it does mean we can cope with up to 25% bit errors, which is a lot of noise. And it varies a lot. In some flights, we get a lot of logging, packets logged that had error correction applied, and some flights, none. It very much depends who else is operating radios in those bands around the time of our flight, and so it's really hard to predict how much the error correction is needed. But it does increase your noise robustness a great deal. Okay, other features that we needed to add. Once we got the basic radio working, we then wanted to start distributing it. It's being sold now by 6 different manufacturers who have adopted the firmware. And in fact, the people who make the base chips and the modules, Hope RF, I wrote to them a little while ago and said, hi, you provide this really terrible firmware as a sample with your chips. Wouldn't you like to provide this much better firmware that's over here on my GitHub site? And I didn't expect to hear back from them at all. You don't normally hear back from Chinese manufacturers when you send them emails like that. I heard back from them the next day. They said, we're already started shipping your firmware because one of the manufacturers requested it to save them having to flash it onto the chips, which is really nice. So hopefully this open firmware will start spreading to people who make garage door openers and all sorts of other things, because these sort of chips tend to get used for. So there's lots of other regulatory compliance stuff that you need to deal with in particular parts of the world, particularly in Europe. Listen before talk, where there's some very strict rules about how much signal is allowed to be out there before you start transmitting. Duty cycle for EU compliance, where you can transmit at much higher power if you only have a 10% duty cycle, and there's very strict rules on calculating that duty cycle, is how often you transmit. As I said, the AT and RT commands are very useful. We also, because we now had the control over the firmware, we could start adding additional protocol features. For example, we can do Mavlink framing, where we deliberately align our Mavlink protocol packets with the radio frames. So when we lose a radio frame, we don't lose half of this packet and half of the next packet, thereby losing both packets. We only the Mavlink packets are aligned directly on radio packet boundaries. And we could do flow control over the air, which is normally quite difficult to do over a transparent serial link. But because we had control over the firmware, we could start propagating flow control information back between the radios and from the radio to the autopilot, and that allowed us to do, send little packets to say how full our buffers are, and it can choose to then slow down its telemetry rates, that sort of thing, which is really nice. So having control of the radio firmware is really nice. It also means that other applications like attaching a GPS and turning it into a position transponder, ARPS type thing is very possible, because you've got full control of the firmware. Okay, then we wanted more range. So the next step was to go to the next radio. We worked with Seppo Sario at RF Design in Brisbane, a really nice little company up there. And he designed the next level of the radio, which is this one. So he basically took the SI1000 and added a 20 dB power amplifier, a 20 dB low noise receive amplifier, a SAW filter, a transmit low pass filter to stop GPS interference, dual antenna. So two antennas with antenna diversity, and it pushes up the power, so it can do 30 dBm legally in Australia, 36 in the US because of the quirky rules. You get ranges easily of sort of 60 to 80 kilometres with Omnis. In fact, probably a lot more. People, if you wanted to go out and do a test, you'd almost certainly get 120 to 150 sort of things if you can get line of sight. It's a little bit tricky with curvature of the earth and stuff. You need high hills. But yeah, little Omni antennas, you can get quite decent range out of these things. They're very nice little radio, very nicely made. I'd highly recommend it if you want a telemetry radio. As far as we know, this is pretty much the premier telemetry radio in the world now. All running our open source firmware, which is really nice. We just did a couple of minor mods to the firmware to support the control of the power amplifier and the antenna diversity, and it was all then working, and that's what we ended up using in our UAV. Although it was way overkill, we were only going about 10 kilometres, so in fact we had oodles of extra range on this thing. Okay, in fact this is the range we got. This is our competition flight for the Outback Challenge. And the green line at the top is the distance from home that the UAV is. You can see it gets up to about 6 kilometres and drops down to about 4 kilometres because it's got a 2 kilometre search pattern. So it's going up and down and searching for Joe. The red line is the signal at the ground station, and the green line is the signal on the plane. It's RSSI units, basically divide by 2 is proportional to dB, approximately, close enough to that. And then you can see the noise levels. The blue one is the noise on the ground station, and the yellowy orange one is the noise in the plane. So you can see we have a bit of a noise problem in the aircraft. It's mostly the electronics, the Panda board, the Linux box on the plane generates a lot of RF noise. It's that we weren't shielded well enough. It still gave us plenty of range. You can see there that the link margin we have is of the order of sort of 50 RSSI, 25 dB type link margin. So if you take 25 dB and divide it by 6, that's 4, so 2 to the 4 is 16, 16 times 6 kilometres, so you're talking about 96 kilometres, so 100 kilometre range we could have got, right, if we'd pushed it right to the edge. And our error correcting code would have been working like mad at that point, but it really is quite long range. We only needed a much shorter range than that. But range testing, testing the error correcting code was quite interesting and quite difficult. It's very hard to get these radios not to get through. So what I did was, first of all, I set the radios with lousy antennas and with minimum power level. 1 dBm is the lowest I could go, so just over 1 milliwatt, 1 point something milliwatt of transmit power. And at first I tried putting the radio inside a fridge. And then I thought, close the fridge, metal all around it, I hoped. Somebody suggested earlier today it might be a plastic fridge. And I found that it still got very, very strong signal. So the next thing I did was I put that same little radio inside a steel casserole pot, completely enclosed, inside a microwave oven at the far end of the house, and I still got far too much signal and I wasn't getting down to the noise. So then I put a 30 dB attenuator that I got off eBay on the antenna connector, and then I was down to the noise level and I could start checking the error correction. But it's really annoying. Air is great as long as you've got enough of it, but you need long distances to actually attenuate the thing down to reasonable levels to test your error correcting. Within a house, if you can't give the radio to your neighbour up the street or whatever, it's actually quite difficult to get your signal down low enough for real testing. I finally found a use for our old microwave oven, which my wife had been trying to tell me to throw out for years because we were never going to use it. Finally. Okay, so that's telemetry. What about images? Well, we wanted to transfer images of Joe down. So now, transferring telemetry and transferring images is very different. Images requires a lot higher bandwidth. How's my time going, by the way? Where's the... Okay, pretty close, halfway through the talk. All right, transferring images is very different to transferring telemetry, and it's non-repetitive data, but it's usually not time critical. And you need guaranteed delivery for critical images, like when you identify your search and rescue target. In our setup, we had one RFD 900 and one Ubiquiti 5.8 gigahertz bridge, and we wanted full redundancy to be able to complete the mission with either radio. So if one radio completely died, we wanted to be able to complete the whole mission. That meant we had to get all our images over this 57600 serial link. Now, images across a 57600 serial link, the raw images from the camera are 20 megabytes a second. So we need a lot of compression. And we still want all our telemetry and command and control to go as well. We had a budget of around 2 kilobytes per second available for sending images across this radio link. But we managed it. So one of the tricks is, first of all, you don't need to send the full image. As long as the image recognition algorithm in the plane is working well and it identifies just a little few pixels around interesting blobs like Joe. This is when we found Joe in the competition. There's Joe. And you only need to send just those little tiny thumbnails surrounding Joe. And then you can actually concatenate them together and compress the hell out of them using JPEG and squirt those across a link, and each one comes down to being less than 2 kilobytes, sort of 1.5 kilobytes or so, which means you can send roughly one of those per second or so across this 2 kilobyte per second link. Okay, but then how do you send it? At first we tried to use TCP, and it was a complete disaster. So we had this initially Ethernet bridge, 1.5 megabit, just run TCP, send the images over that. Gosh, it was awful. The problem is that TCP handles packet loss extraordinarily badly. We basically found that at about 20% packet loss, TCP just stops. It doesn't restart for a very long period of time. And even we tried all of the different congestion control algorithms. There's like 20 of them available in the Linux kernel. None of them did anything much more than sort of 25% packet loss before it crapped out completely. So completely useless. So we looked around for all sorts of other algorithms and protocols for transferring data reliably across links that sometimes have very high loss levels, because this link, occasionally, when the propeller and the motor was between it and the ground station, might have had 90% packet loss. And we wanted to keep getting, when it has 90% packet loss, that's 10% packets that are getting through. You want to get 10% of your theoretical bandwidth, right? You want to be an efficient link. It's not acceptable to get 0% just because you've lost a few packets. So we came up with a new protocol. And we don't know if this protocol is completely original. I mean, we made it up ourselves. We don't know if anyone else has done it. But it worked for us, and it gives us a protocol that is completely efficient in the sense that you've got 90% packet loss, you get 10% throughput, and you have complete control over the bandwidth and over bandwidth and segment size. You can encapsulate it over UDP or Mavlink or pretty much anything. Carrier pigeon would be fine. Now, basically, it's very different from TCP. It's a greedy use of bandwidth. So if you aren't sending in a point-to-point link between a UAV and the ground, you're wasting bandwidth, right? You're always sending, because you've got a dedicated link, a point-to-point link, right? So very unlike TCP, where you sort of try and avoid sending, this thing always is basically sending all the time. The acknowledgement system, the sliding window type system for TCP, really awful for this sort of thing. So we instead used an extent-based acknowledgement system, similar to the extent-based in file systems like ext4, where you have basically an acknowledgement packet which has a list of pairs of 16-bit numbers. In fact, I'll show you what it looks like. These are the packets. So there's our chunk of data coming through. We basically have these two packet types. This block extent is actually an element of this block ACK. So our block chunk has a block ID, which is basically like a file, an image, or a Python object. We were sending Python objects over this. And then our block size, how big the overall file is, chunk ID, chunk size, and the data. Then the acknowledgements is the key. It's a set of extents, start and count, allowing you for sort of non-contiguous acknowledgements of packets. Then you keep a set in Python. We've also now got a C implementation, of which chunks within a block have been acknowledged so far. And works incredibly well. Another aspect of it that's quite important is what chunk do you send next? My apologies for rushing here, low on time. We basically keep an estimate of the link round trip time, just estimated from the packets that have got through. And then we send the first chunk in any block that is in the queue that has not been sent within the last round, within the estimate of the round trip time of the link. So that means we have multiple files in flight at any one time. We quite often had 200 or 300 images in the queue on the send side. And the images would build up when we're going away from us because the engine was between us and the antenna. When it turned around to start coming back, those images would flood down rapidly as the queue drained because the packet loss rate would plummet. And yes, we should have had twin antennas, one out on either wing. We didn't, but it worked anyway. You also have optionally ordered delivery you can ask for, and you have priority. Every block you send, you can say what the priority of that block is in terms of whether it jumps the queue, the transmit queue, which allows us to set the priority of an image based on how well it matches Joe. And that allows the important blocks to get through first. And this gives us a really easy protocol. And it worked extraordinarily well. We found that we were able to quite happily send images reliably in sort of the sideband of these 57600 radios, as well as at high bandwidth, up to megabits per second over this radio when we had a good link. So it scales from kilobits up to megabits quite happily, and its efficiency is essentially exactly whatever packet loss. You've got 70% packet loss, you get 30% of the bandwidth of the link. So that's that. It's available as blockxmit.py, a Python implementation, and there's a separate C implementation which isn't quite working yet, which we're putting on our autopilot board, on little ARM boards, embedded implementation. Okay, so I'm just about out of time, I believe. So more information, all of the code, of course, is available. The firmware, SIK for SI1000, that's the chipset on the radios, that's available there. The 3DR radios themselves, information, all the schematics and things for the radios are all available. RFD 900 is RF design site up in Brisbane. BlockXMIT code is sitting there, the Mavlink protocol, and of course the Canberra UAV site.